Perfect. So hello everyone, welcome to the event. Thank you for joining us today, and we look forward to talking to you about our topic of life cycle assessments today with our wonderful speakers. Before we get started, as Chloe, I think, messaged in the chat while you guys were waiting, this meeting is recorded, so by being here, you are giving us permission to record you. If you're uncomfortable, you can turn off your cameras and that's totally fine, but just as a heads up for that. So before we get started, we just want to introduce the team. So this is our team. I'll have each of them introduce themselves, but my name's Gagan. I'm a student at McGill, and that's where I'm joining from today. And I'm a part of this team, and I'm very excited to be hosting this event.
Yeah, my name is Sarah. I'm also one of the organizers here in Graduate Student Liaison Beyond the Nine. I'm also at McGill University in Canada. That's where I'm situated today. I'm really excited to be here.
And hi, my name is Jasmine Hong. I'm also a graduate student at McGill University, but I'm actually meeting with you guys from Switzerland as I'm at a workshop on microplastics at the moment. But I'm really excited to hear the conversation today.
Hello, thank you guys. And then we have our faculty support that are, I think Professor Cynthia is here, so if you want to introduce.
Yes, so hi everyone, my name is Cynthia. I'm an associate professor at the Institute of Chemistry of São Paulo State University in Brazil. And it's a pleasure to have you all here today. I'm really excited as well.
Perfect. And then I think our other faculty support is not here right now, but she's also helping us from Nigeria and helping us support from there as well whenever she's able to join today. And obviously this event, we have many sponsors. One of them is Sigma, and they're supporting our connections throughout the year. If any of you guys have any contacts who would want to sponsor us, please reach out to us. We would love to have some support.
So we'd like to begin with a land acknowledgement. So as mentioned earlier, a few of us are situated at McGill University in Montreal, Canada. So we just like to take time to acknowledge the land. So McGill University is located on land which has long served as a site of meeting and exchange amongst Indigenous peoples, including the Haudenosaunee and Anishinaabe nations. McGill honors, recognizes, and respects these nations as the traditional stewards of the land and the waters on which we meet today. And we are in a bilingual country, so we do also have the French version.
Yes, l'Université McGill est sur un emplacement qui a longtemps servi de lieu de rencontre et d'échange entre les peuples autochtones, y compris les nations Haudenosaunee et Anishinaabe. McGill honore, reconnaît et respecte ces nations à titre d'intendant traditionnel de terre et de l'eau sur lesquelles nous nous réunissons aujourd'hui. Merci.
And see you too.
Well, I'm sorry.
No, go ahead.
So I'm speaking from Brazil, and in the spirit of reconciliation, we pay respect to the indigenous people of Brazil, who are the first knowledge holders of this land. And presently, this meeting place is still home to more than 300 indigenous nations, and we honor, respect, and celebrate the diversity of peoples connected to this land.
So in terms of logistics, you can add pronouns to your Zoom name if you haven't already by just selecting rename from the drop-down menu. We also do have a live transcript enabled, so you can click CC at the bottom of your screen. And we also have the slides and transcripts available after today's connections if you would like to access them later. So for code of conduct, this is a very diverse and inclusive space. We want everyone to feel a strong sense of belonging during the connection, since the whole point is to connect with people all over the world. So we expect everyone to remain professional, respectful, considerate, and mindful of all the different people joining us here today. And we will not tolerate any harassment, bullying, abuse, or threatening behavior.
Awesome. So just we want to go over the agenda for today before we get started. So we'll have first just our welcome introductions, which we've done, and then we'll have our two speakers speaking at the beginning, around 15-20-minute presentations each. Then we'll have breakout rooms with the individual speakers themselves. So if you have any questions, you can ask them during the breakout rooms. And then we'll also have some breakout rooms for the Beyond Benign and our connections team as well. Then after a short break, unfortunately, our third speaker cannot join us today, so we'll have some updates and then again do breakout rooms for if you have more questions for the speakers, or we'll end slightly earlier than I expected. So yeah, before we can get started with our first speaker, which is which is Professor Dr. Philip Jessop. He is a Canada Research Chair in Green Chemistry at Queen's University in Canada and an Executive Research Director of Forward Water Technologies Institutions. His research interests include green solvents, biomass conversion, and CO2 responsive materials. He also has distinctions including the NSERC Polyani Award in 2008, Canadian Green Chemistry and Engineering Award in 2012, and the ENnie Award in 2013, the NSERC Brockhout Prize in 2019, and fellowships in the Royal Society of Canada, the Royal Society of Chemistry, and the American Chemical Society. He serves as a chair in the editorial board of the Journal of Green Chemistry from 2017 to 2022, and has chaired in 3 major international conferences and helped create 2 spin-off companies and Green Centre Canada, which is a center for the commercialization of green chemistry technologies. He also has a TikTok series called Jessop's What is Greener, which has reached over 10,000 viewers. So please join me in welcoming Dr. Jessop.
Thanks very much. And I couldn't figure out the rename thing, so my pronouns are he, him, and I'll do it when I figure out how to do it for my name. But I'm delighted to join this event. Oh, somebody did it for me. Thank you. Great. Yeah, so I'm going to tell you about LCA-based research, and let me figure out how to share screen here. That shouldn't be so hard. Can you see it? All right. So life cycle assessment, we're going to be hearing more about that in the next presentation. So I'm going to be a little bit light on the details of life cycle assessment. But I think it's really important in green chemistry because it allows us to compare worse options to better options and figure out which ones are worse and which ones are better. And so I really believe that this skill is so important in green chemistry for whether we're talking about training for students or researchers or the public, determining which of several options is the greenest option, the least environmentally harmful option is the most important skill in green chemistry, in my belief. And it's not just for green chemists. Like that TikTok series, I've been trying to help the public understand how to decide between, plastic straws and paper straws, or electric cars and gasoline cars and this kind of thing. But let's suppose that someone is working in industry and they're going to build a new plant, and there's several ways of making the product, and all of them are going to make oodles of money. And so that's not the deciding factor. So the deciding factor then would be we want the one that's the greenest. And so how do you figure that out? How do you identify which of the available options is the least environmentally harmful? And that skill, I think, is the #1 most important green chemistry learning objective. And that this skill is to identify the ability to identify the least harmful of available options. And if students in green chemistry don't get that skill, then I don't think we have succeeded in teaching the students green chemistry. And I think this skill can be embedded in first-year undergraduate courses, maybe even in high school. Am I cutting out? No, I'm okay, good. So I really believe that this is the most important thing we need to teach beyond anything. And I don't think we should reserve this learning objective to specialized green chemistry courses. We need to put it into first year, maybe even into high school. But the problem with that is everybody says, oh, you can't squeeze anything else into first-year undergraduate chemistry because the curriculum is already full. There's all sorts of important stuff in there, and you can't put something else in there without displacing one of those existing important topics. And so everybody screams murder if you try and add something. And so I want to show to you today how we can get green chemistry and this important skill into courses and into research without having to go through a great deal of trouble or displacing existing content. So the important thing we're trying to teach here is, let's see if I can move this out of the way, is the skill of just determining which of several options is the greenest. So let's suppose that the company is going to be converting hexanol into hexanal. That's the process we want to do, but there's several options on how to do that. And what we want to be able to do is to say which of these three options is the least environmentally harmful. So how do you do that? And so the standard way we teach metrics, green chemistry metrics in university, is the mass-based metrics like E factor, atom economy. There's a bunch of others. Here's a list: process mass intensity, yield, regular old yield, and there's also effective mass yield. Lots of different variations. They're all about mass. And when we tell students this is how green chemistry works, you know, we compare the two or more options in terms of mass. What we're teaching the students is that green chemistry is all about the avoidance of mass, which is not really what green chemistry is about. Mass doesn't tell us about harm, right? And so that's the fundamental problem with mass-based metrics. There's actually two fundamental problems. One is they tell us nothing about harm. You know, if one causes more mass to be released than the other, does that mean there's more harm? And the other thing is they never consider energy consumption, which is often, and especially in life cycle assessment, you'll find very frequently that the energy consumption is very important in determining the overall life cycle harm of one or more of the options. So those two flaws in mass-based metrics make them, in my opinion, nearly useless for predicting which option is the greener option. And so when I present this slide in my classes and I say, okay, so here's the options and here's the E factors. And just remember, E factor is defined as the mass of waste over mass of product. So a large E means a lot of waste. And so we want a small E factor. So I say, here's your three options. And you can see the E factors for each of the options. Which one is the green one? And I'll leave that open and ask the students to comment. And the students invariably say, you can't tell. I mean, it looks like option C has the least waste in terms of mass, but that doesn't tell us anything about harm. That could be really nasty stuff, whereas the waste coming out of option B might be greater in mass, but it might actually be less harmful stuff. And so you can't look at this mass-based metrics and determine anything about which one is the greenest option. And so for that reason, I believe we're making a mistake when we teach students mass-based metrics. I think we should either replace them with impact-based metrics, or we should do both. But just sticking with mass-based metrics is doing our students a disservice and badly representing what green chemistry is all about. But impact-based metrics are not popular because they're seen as being less easy to do. They're seen as being horribly difficult. And that's because the standard impact-based metric is called life cycle assessment. And it's a heck of a lot of work. You know, it takes months to years to do a proper LCA, and that's not something you can squeeze into a couple of minutes of lecture time, right? It's too difficult. It's not that we don't do it. Yes, people learn about this. You can take an entire course on life cycle assessment. You can become an expert. You can do grad studies on this, but you're not going to squeeze it into a couple of minutes of the first year undergrad curriculum. So this is what you get out of a life cycle assessment. You've got your multiple options 1, 2, and 3, maybe a new option you've developed of a new way of converting hexanol into hexanal. And for different environmental impacts like acid rain formation, smog formation, global warming, the life cycle assessment gives you numbers for each of the available options. And it looks like for acid rain formation, it looks like the new process is the greenest. Great, fantastic. And it looks like option 3 is the worst. And then you can look at all these other environmental impacts and decide for each of them which option is the best. And then you have to decide, okay, which of the options are we going to go with? Which one is the actual greenest one? And sometimes it's obvious, and sometimes it's some You have to do some trade-offs. But that's what life cycle assessment gives you. And nobody wants to do this in undergrad chemistry because it's kind of complicated and time-consuming. But it doesn't need to be. So here's basically how LCA works. We'll hear more about this in the next presentation, I'm sure. But basically, you take all the different life stages in the process of getting, mining the resources or agriculture, refining those resources, making commodity chemicals, fine chemicals, making the product, wholesale and retail distribution, use by the customer, and then disposal or recycling. That's the whole life cycle. And each of those stages in the life cycle has inputs and outputs. And each of those inputs and outputs can cause harm. Okay. And that's why life cycle assessment is so intimidating in terms of amount of time required, is because you have to make lists of all the chemicals and all those inputs and outputs and quantify all those things and then start calculating how much harm. And that's why it takes a lot of time, right? The actual math for calculating the harm is trivially simple and takes very little time. It's the data collection that's intimidating and time-consuming. And that's important because the fact that the math is trivially simple means we can implement this in the first-year undergrad curriculum. Just don't make the students do all that data collection. And then they can do it. So here's the equation. This is the math. If you can multiply, you can do impact-based metrics, okay? So here's the generic equation. The harm, which is I, is equal to P times M. So M is the amount of chemical released as one of these outputs from one of the life stages. So let's suppose we're releasing 1 kilogram of methane or something, okay? That's the mass of chemical released. P is the potential, which is technically a unitless number. It tells us how harmful 1 kilogram of this chemical is compared to a kilogram of the reference chemical. And for global warming, the reference chemical is carbon dioxide. For acid rain, it's sulfur dioxide. There's different reference chemical for different impacts. But P just tells you, methane, for example, has a global warming potential of 28, which means releasing a kilogram of methane causes 28 times more global warming than a kilogram of CO2. And finally, the I is the impact, the harm caused by releasing that much chemical. So that's it. That's impact-based metrics right there. So if you can teach I equals P times M to your students in first-year undergrad chemistry, they are now equipped to do those calculations, right? So that won't take very much lecture time. And so here's the equations for individual impacts, like global warming. The impact for global warming is the potential for global warming times the mass released. If you're more interested in ozone depletion, it's the impact of ozone depletion equals potential times mass, right? For every single impact, it's just the potential, the corresponding potential times the mass released, right? So really the math is not difficult, all right? So here's the usual impacts and potentials people want. Here's the reference chemicals listed for the most common ways of doing it in LCA, and these are the units. But the problem is that instructors, the average instructor, doesn't have access to all these potentials. They're hidden in databases and very expensive subscription-based software. So where's the average instructor going to get these potentials? All right, so here's some sources. You don't have to go through some detail right now, but basically, I'm writing an article, I'm about to submit it to JChemEd. It'll have a huge database attached to it in the supplementary material for potentials that instructors can use. You can also look at some older data from this book in 2001, has a lot of data. For global warming, there's lots of data here and smog formation here. So those are some easy sources of potentials that are already being calculated for you. Now, here's an example of how you can use this in first-year undergrad chemistry, a simple example. What we want to do is to take questions that the students are going to have to do anyway. For example, learning how to convert moles into grams is a standard skill that people have to learn in high school or first-year undergraduate chemistry. And so we're going to take that exercise that they have to do anyway in first-year undergrad, and we're just going to tag on one more line of calculation to get them to calculate the harm. So they're already calculating masses. So for example, this question says, if we talk about venting methane, you can either burn it as you vent it, that's called flaring, or you can just release the methane as methane. Which one's going to cause more global warming? Or which one's going to cause less, right? So you give the potentials, and then the answer, the students, all they do is they convert moles to mass, which is that practicing that first year undergrad skill that they need to practice anyway. And then they have one extra step of calculation. Sorry, this 23 should have been a 28. You multiply the mass you just calculated by the potential, and it gives you how much global warming. You do the same for the other option, and then you compare which one has the less global warming. So really, this is giving them practice in moles to mass conversion, which is already in the undergrad curriculum. They just have this one extra line of calculation, which is based upon that generic equation, I equals P times M. And this gives them the chance to make a comparison between two options and decide which one causes the least environmental harm. Okay, so this can be done in the first year curriculum without adding lots of extra new content. Now, this second example is a much more complicated example, would be better for second or third year organic. And it shows a comparison of two syntheses. Now, traditionally in organic courses, we would compare two syntheses in terms of yield or rate or selectivity. But this allows us to compare the two options in terms of environmental harm. So this particular question says, here we have these two syntheses of the same product from the same starting material, and it makes some acid waste or potentially acid rain forming waste like unreacted ammonia or these byproduct gases. Here's the acidification potential, how much they cause acid rain. And the answer is you just calculate mass again for each of the chemicals and then multiply by the potential to get the total amount of acid rain caused. And then you compare the two options and decide which one causes less harm, right? This is a more complicated example, so probably second or third year, but it's the same idea. We're using that very simple equation, I equals P times M, to calculate and then compare harm for two or more options. Now, if you can do this, it's not a big leap to go from that example to teaching simple LCA calculations, right? So that's what I do in my courses in third year green chemistry and in the American Chemical Society summer school in green chemistry and energy. Every year I teach life cycle assessments, and using this math, which is the basis of real life cycle assessments, but it has to be packaged in a way that's not too onerous for the students. You can't expect them to do huge amounts of data collection because they wouldn't have time. But you can give it to them in a relatively packaged format that keeps their time commitment down to a reasonable amount and still gives them the idea of how it works to do an LCA. So what I do is I give them a 90-minute lecture on how LCA calculations are done. And then I divide them into teams of 5 to 7 students, depending on the size of the class. And each team is given 5 literature syntheses of the same transformation. So this example is benzene to aniline. So one team would be given 5 literature preps for benzene to aniline. And they're asked to do LCAs for all 5 of those, and then compare and decide which one of those 5 options is the greenest synthesis of benzene to aniline. Other teams would have different transformations. And so all of these are literature preps. I package it so that it's relatively easy. If there's a bit of missing information, I tend to slip it in so the students don't have to go around and start doing literature searches. And then each team does a gate-to-gate LCA for each of the 5 syntheses. And gate-to-gate is not the best way to do LCA. In fact, it's quite flawed. It's much better to do what's called cradle-to-gate, which is all the way from resource extraction to the product. But we do gate-to-gate because I'm trying to keep the time commitment of the students down. And I warn them, this is not as good as doing cradle to gate, but this is why I'm making you do gate to gate, okay? And they can even bring that up in their discussion afterwards that we might have gotten a different answer if we'd done cradle to gate. But this allows it to fit into a reasonable time commitment. So they do a gate to gate LCA for all 5 syntheses, and then they report their result in a table just like you would get in a regular LCA. And then, they present this to class, each team, and they argue in favor of one of the 4 syntheses being the greenest one. And that gives them practice in debate and trade-off. Usually there's not one of them that's fantastic across the board for all the impacts, so they have to make some trade-off decisions. Which one are we going to go for? One last concept I want to introduce. I'm almost out of time, so I'm going to shut up very soon, but I just want to bring one more concept. That while this kind of work can be done in LCA light, can be done, and impact-based measures can be done in research as well. It's not just for the educational crowd, right? You can do If you can't afford a full LCA and you don't have the training or available resources for that, you can estimate the impacts of your various chemicals in your process using these impact-based metrics. If you want the slides from my 90-minute lecture on LCA, just write me, I'll send you the slides, that's fine. But just using LCA, now this is talking real LCA, where you have all the life stages, cradle to gate or cradle to grave. You can use that in research if you have it available to you. So if you can get someone to do an LCA, or you find a literature LCA that's relevant to your research, the LCA can be wonderful in helping you choose your research project. Let me show you how. If you look at all the different stages in a product's life cycle, all the way from the stage 1, which is like mining and agriculture, all the way through when the product is leaving the factory property, which is the gate. You can look at all those stages and identify from the life cycle assessment which one causes the most global warming or which one causes the most acid rain. That's called the hot spot, okay? So if you can identify which stage causes the most harm, that's the one that needs to be prioritized for green chemistry research. If you're going to spend time, money, and chemicals on research to make something greener, pick the one that does the most harm, right? So if you were to run around and make stage 4 greener, it's not going to do much, right? It's a waste of time, in my opinion. So it's really important, I think, to prioritize the stages that cause the most harm. And so that's what I call hotspot-driven research. If you want to learn more about that, there's a paper that's it's online already in green chemistry, but it's not got page numbers yet. So I also do this kind of education for the public because they got to make decisions too. They're deciding between an electric car and gasoline car, or butter versus margarine. And so I use TikTok videos to teach this to the public. In the picture here shows a regular burger versus one of those Beyond Meat, what's it called? I've forgotten what it's called now, but it's one of those plant-based burgers. And as long as you have all the works on it, I think it tastes the same. If you just eat the patty by itself, it does taste different, I admit. Anyway, so which one's greener? I do different kinds of transport and other topics, and I don't show them the data table. Never show a table of numbers on a TikTok video because you lose your audience immediately. So what I do is I show my kitchen table instead. And each of those numbers in the table is represented by either balloons or whatever. This is the particulates put into the atmosphere. And I just use crushed charcoal briquettes. And for showing how much smog, I use gold-colored or brown-colored balloons. For showing how much CO2, I use red-colored balloons, each of them inflated to the right size to indicate how much CO2 is being produced. And this allows the audience to make the comparisons between the options without pissing them off by showing numbers. Finally, I think, concluding thoughts, I think the most important green chemistry learning objective for students, for researchers, and for the public is the ability to identify the least harmful of possible options. Impact-based metrics teach that skill to students. Mass-based metrics don't. Impact-based metrics can be taught as part of the first-year undergrad curriculum or even in high school without displacing existing content because the math is so trivially easy. It can be slipped into the end of existing questions. LCA can be taught in upper year courses, even though we might have to sacrifice like cradle to gate to make it into just a gate to gate, but it can be taught and the students learn a lot. And I've got a lot of really good feedback from students from this. And finally, impact-based metrics can be used by researchers as well, not just students and instructors, even if they don't have LCA training. But of course, the first option is always to work with an LCA person as the best option. Thanks very much. Happy to take questions.